Good afternoon, good afternoon. We'll get started in a couple minutes here. Hello everybody. In just a second here, we're going to talk about our project. It is the first of two projects that we'll do. Good afternoon, Phil. Good to see you. How's everybody doing? You guys doing all right? I hope you're doing all right. What do you say we talk about Project One a little bit here? Like I said, it'll be a short lecture today. I don't plan on introducing any new content. I just want to show you Project One and give you some idea of what to expect. So it's already up on UB Learns. So let's get this picture in here. We are going to analyze the dynamics of a quarter car suspension model. So it's quarter car because it's 1/4 of the top, 1/4 of the car. It looks at one tire and the suspension elements at that one tire. So the model accounts for the stiffness and the damping of the tire. You can see a little damper and spring down there, and that represents the stiffness and damping of the tire itself. And it also represents the stiffness and damping of the suspension system. So those parameters are KS and CS. All right. So if you imagine pressing down on this mass a little bit, the spring's going to sink in, the damper's going to sink in, the tire itself is going to deflect a little bit. So this can kind of bounce a little bit in the vertical direction. And that's what it models. So, okay. As the car travels with some velocity v towards the right, it's going to encounter these sinusoidal bumpy hills. And each bump has a height h and a width L. So you can imagine what happens. The tire goes over this bump. The road presses up on the bottom of the tire. And then the springiness of the tire itself will react to that. And that'll transmit a force to the wheel hub. And then the suspension linkages will then get an additional force from the hub motion, and that'll get transmitted to the car up above, which is also called the sprung mass. So one rule for this that'll simplify the dynamics, we're going to assume that the bottom of the tire is always in contact with the profile of the road surface. So if I run up this ramp, I'm not going to allow the tire to actually fly off and get some air time. Although that would be kind of fun, wouldn't it? But no, we're going to assume the bottom of the tire always has to follow this contour. It's stuck to the ground. Okay. And I make a little note here. Because the tire, we're modeling that it can compress and stretch a little bit like a real tire. This vertical motion of the bottom of the tire as it goes over this profile, that could actually be a little different than the motion of the wheel hub. Because they aren't rigidly connected, there's some springiness there. So that's why I have separate variables, like this R of T is the vertical motion of the bottom of the tire. W of T is supposed to be the vertical motion of the wheel hub. And X of T is the vertical motion of the sprung mass. All right. So this next part here, I have some expressions for R of T. So R of T is the vertical motion of the bottom of the tire. This is what R of T is going to be if we go over these bumps with some constant velocity V. So you'll see V shows up in here. The height of the bump is here, the length of the bump. So this velocity affects the frequency with which we're hitting these bumps here. Wait, I might have to fix this. I'm skeptical of what I did here because this V is in the denominator here. And that means that the faster I go, the bigger V gets, but the smaller this number becomes because we're dividing by V. But this number is the frequency of oscillation. Shouldn't the frequency be faster the faster I go over these bumps? So I'm going to have to go back and check my math right here. Because I think that V might need to be in the numerator. Okay, I'll check that. But either way, hello UB Math Prof. Welcome. So this is an expression for the motion of the road as we travel over it. Next, we have, using Newton's second law, the equations of motion. So this first equation, equation 3, you get this from summing up all of the forces acting on the sprung mass. So the weight of the car, mg, is going to be pulling it down. The the spring is going to be, well, okay, if the wheel hub goes up, then that's going to generate an upward force through the spring on the sprung mass. But the amount that the spring is actually deflected is the difference between W of t and X of t. That's why I put this subtraction here. Maybe I'll zoom out a little. It's easier if you look at the picture. So yeah, like I said, if WT goes up, that'll squish this spring, and then that spring will want to push up the mass. But the amount that the spring is actually squished is the difference between those two. So similarly with the damper, the force produced by the damper is based on the relative speed between the wheel hub and the sprung mass itself. So that's the sum of forces on the sprung mass above the suspension. And then the second one is the sum of forces on the wheel hub. So this is the mass of the tire and wheel like combination. And this is a little bit of a longer expression because you have the suspension spring and the suspension damper acting on the wheel hub, but you also have the tire. So I have the stiffness of the tire and the damping coefficient of the tire. So this expression is a little longer because if you look at the wheel hub, it's got these springs connected to it and also the tire springs are connected to it. So it has forces from all of those different components at once. Whew. Okay. So I went all out on this, okay? Because I tried to look up realistic values for all of the terms in the equations. So if you're wondering like how stiff is the suspension spring in my car, well, this is like a typical value for a passenger car. It produces 30,000 newtons per meter of deflection. I mean, you'd never deflect this an entire meter, but you can see that's a stiff spring. It can produce a lot of force. Your tire is actually way stiffer. It's like an order of magnitude more stiff than your suspension spring. And the tire is less damped. So I think the suspension system itself, it has a damping ratio of like 0.2, but your tire has a damping ratio of like 0.1. So they oscillate quite a few times before they settle. That's just what a low damping means. The quarter car sprung mass, 400 kilograms. So this is like the weight of a fourth of a typical car. If it was a Tesla, it would be even heavier. If you guys are familiar with Teslas, the battery in there, it is immensely heavy. It weighs a lot. But so this isn't a Tesla, but that's just a fun fact. Teslas are like super, super heavy relative to other cars. Okay, so let's get into the deliverables of the project. We've been doing state space form. The first thing you're going to do for this project is put the equations of motion, equations 3 and 4, in state space form. And I want you to use these states. I want you to use these outputs. And these are our inputs to the system. The position of the road surface, the rate of change of the road surface, and also I'm including gravity in there. Our outputs are the vertical position of the sprung mass, the vertical position of the wheel hub, so we'll get like the relative motion of those. And this last output, this third one, is the force in your suspension system at any time. So it's like the spring times how much it's compressed, plus the damper multiplied by how quickly it's being compressed or extended. So we have a fourth order system with 3 outputs and 3 inputs. Based on the sizes of these vectors, you can determine like how big the A, B, C, D matrices need to be. Okay? So that's the first step. Put it in state space form. Once you have state space form, here's the second part. I want you to get the system roots. I gave a little hint here. I hope you remember the system roots have something to do with the A matrix. I'll just leave it at that. But once you have the roots, there's going to be 4 of them. I want you to get the damping ratio and natural frequency for each pair of roots. I want you to tell me which roots are the dominant roots. And I want you to give me the system settling time. So you can get all of that information from the roots. So not too bad. This next part's kind of cool. We're going to calculate the effect of gravity. So we know the weight of the vehicle causes the car to compress your suspension system and the tire a little bit. Here, we're going to calculate exactly how much the tire and the suspension get compressed by the weight of the car. We're going to use the step command to apply a step input for gravity. Well, gravity's always acting on us, but we're going to simulate as if like, okay, I'm just going to turn on gravity onto this suspension system. I'm going to activate the weight of the car. Boom. See what happens. We're going to assume for this problem that the vertical motion of the road surface, R and R dot, those are just 0. So this is just going to be a car sitting on the pavement. We're just going to turn on the weight and see what happens. So the only input we're considering is the effect of G. Like I said, this will simulate the car being dropped onto its suspension. And you can probably imagine what that's going to look like. It's kind of going to like settle in, and eventually it'll just come to rest. So that's where we're simulating. And what I want you to plot is X of t and W of t. So those are our first 2 outputs. That's the motion of the sprung mass and the motion of the wheel hub. Because they're not going to move a lot, I want you to convert these units to millimeters. In the equations of motion, the units are in meters, so you'll have to do a conversion to change it to millimeters. Yes. For feedback, I'm also including in here what your final results should look like. So if you go 1 page, I'm showing you the plots that I'm getting. The reason I do this is for feedback, so that you can know when you're simulating everything, am I getting results the way they should be? So you might run your code the first time, you're getting some errors, and you finally get it to run, and you get plots, and you're like, does this make any sense? Well, you can come here, you can compare it to this, and that'll be some feedback for you. I think that's important for learning, to have that iterative feedback. Okay, I won't get too much into those right now. In this box, I put some hints because this is a little bit more complex, it turns out, than stuff we've done so far. So, yeah, this first hint is just about the step command. Actually, you guys know how to do this. The second hint, because we have 3 inputs to our system, the way I've defined everything, when you use the step command in MATLAB, it'll give you back 3 sets of outputs for like the case of if you gave a step input to one of your inputs or your second input or your third input. It gives you back the result for all 3 of those cases. But we're only interested in this case in the effect of gravity. So we just want like the 3rd set of outputs from the step command. So if you use the syntax I tell you up here, you can get that 3rd set of outputs by calling the 3rd index of this 3-dimensional matrix. Okay, and then once you get these outputs, it's going to have 3 columns. 1 column for each of our system outputs. So one output is the position of the sprung mass, one's the position of the wheel hub, the other is the force in the suspension. So I show you here, if you want to pull out one of those inputs, this is how you can do it. And this is how you can plot it. The last note, the step command in MATLAB calculates the unit step input. So that's a step input that has an amplitude of 1. But if we're looking at the effect of gravity, this is going to provide a step input with amplitude 9.81. So you need more than a unit step input. So I give you a little hint here. You're going to have to use the scaling property to get this effect of having an amplitude greater than 1. So it's cool. You get to see the suspension drop in, sink in a little bit here. You see this oscillation. And you see the force go to a specific value. I should add a question about this because it makes cool physical sense, the value that this goes to. Okay, here's the last part, and I still need to fill in some details on this. So I made a little note here that I'm going to give you some additional hints and feedback for this last part. But here's the fun part. We're going to take this car, we're going to travel over those bumps. So I say in the previous part, we discovered how much the suspension in the tire compresses from the weight of the car. Now we're going to simulate the motion as we travel over these sinusoidal bumps. I'm just defining the velocity to be 20 miles per hour. The height of the bump is 0.15 meters, which is like 6 inches. The length of each bump is 2 meters. And so we're going to simulate the response of the suspension in this case. But we're going to be supplying 3 inputs simultaneously. All right. You have 1 input from gravity. You have 1 input, which is the position of the road surface, how it's changing. And you also have the velocity change of the road surface. We need all 3 pieces of those information to accurately simulate the suspension. So yeah, I'm going to fill in like specifically what I want you to plot here. And I'll make like a little box again with some hints, and I'll give you the graph that I get so you can have a little feedback. And that's the project, ladies and gentlemen. I think it'll be fun. It's a realistic project. This is the kind of simulation a car manufacturer needs to run to like tune their suspension system. They'll probably put, I guarantee they'll put a little more detail into it. But this is the basic exercise. What questions do you have? Concerns? This is on UB Learns right now, so you can look at it. I'll finish it up this afternoon, but I mean, you can start on the beginning parts at least. Oh, the due date. What is this? You have a week. Is this in place of homework this week? We're not having any homework today. I think we're going to have one homework in between this due date. So you're until Wednesday of next week, you're just going to have this. And then I think one homework in there as well. But it'll be like a smaller homework. Obviously, the emphasis is on this project. Thank you for your question, Phil. What other questions do you guys have? This is all we're doing today. I just wanted to talk a little bit about this project to give you some pointers. Is LaTeX required for this project? No, but for you it would be. And I wouldn't allow you to draw your figures using whatever that thing is called. You have to draw them in Microsoft Paint. That's what I would make you do as your punishment. Any other questions, my friends? I mean, I guess you're just seeing it for the first time, so you can't have had much time to process anything yet. But you know, we'll be able to talk about this on Thursday. We can talk about it on Friday a little bit, Monday and Tuesday. So take advantage of those office hours. I'm on here at least for a little bit every day, and then you can always send me email as well. That's right, UB Math Prof. You can't use ticks. Why would you ever draw a figure with code? Phil says, I actually like the idea of real world application. Me too. Me too. And that's why I'm trying to do this project, trying to make it as realistic as I can. And I will continue to do so for the remaining 2 weeks of this class. Whew. This is a very quick timeline. A 6-week course in system dynamics, but you guys are doing very well. So thank you for all of your hard work. It makes me proud. Did you guys hear about UB's plan for the fall? It looks like we're returning to campus, at least in some capacity. It won't be back to normal. It looks like classrooms are going to be 25% capacity. UB Math Pro says TICS allows us to draw in spherical coordinates better, by the way. Oh, come on. You could... No. This doesn't even look right. Isn't like you have this line and then it just changes directions. Is that this thing is all warped? Oh, that's without. Oh no. You tricked me. You tricked me. All right, let's go there. Ah. Great. Okay. That does look nice, but I guess something like this, you need a computer program to draw it. This is a good use of that. I can't fault you for that. Yeah, UB's going back. It looks like with 25% capacity, but certain classes are preferred over others. So I think probably most instruction is still going to be online. That's what our department said, because they said the rooms have to be 25% capacity. That sounds classist. Wait, what do you mean by that? Because if it's like that 6 feet apart thing, that's like every other seat, every other row. Only some classes come back. That's right. Oh. You made a pun? Oh my god. Yeah, okay, anyways, it seems like wait, maybe I can find that email. Okay, labs, you know, like hands-on stuff, those have preference. Clinical training, studio, some graduate research courses have preference. And then, you know, first year seminars, small group instruction, discussion courses, all of those have preference for in-person classes. But think about this, like, so I'm going to be teaching flight dynamics in the fall, and that has 60 students. If every student wants to come to class, and I can only have 25% capacity in that classroom, that means I need a classroom that seats 240 people. We don't have that many rooms that can do that. Who sent this email? President Tripathi? This one was from my department chair. This one was from the MAE department chair. And our department chair was also on some of the planning committees. So I think she's in the know. I see, we haven't gotten emails except for the university-wide ones. Okay, so you only got the Tripathi email, which didn't say too much, just like reduced capacity, but No, the email I got says 25%. That's brutal. I don't know. What do you guys think? Do you guys have opinions on this whole thing? I'm not sure if I'm teaching in-person classes because it just seems like such a risk for the pay. For me, it's if I'm teaching a class where I already know that some students are in person and some students are online, then I have to make online content anyways for the online students. So why not just do purely online? That's kind of where I am right now. Because money. Yeah, it's like it basically, okay, before all of this went down, we would teach in a classroom. Oh, Dr. Strudel says most aren't as good at creating online environments. It's a challenge. I think we're all still figuring out the best mode. I think Twitch is fantastic. Plus, many students are from large cities like New York City. Yeah. If I'm using Twitch in the fall, which I think I will be, at least to some degree, definitely gonna make a green screen. Not too hard to do. Could you go over the second question of the last homework? Certainly. I certainly can. This system is unstable. Though that wasn't my intention, to be honest with you. Let's pull this up. My other class has a terrible teaching style, just clicking through PowerPoint files. I'm not a fan of PowerPoint. Well, in YouTube videos, what do they call it? Death by PowerPoint. No, I'm not a big fan of clicking through PowerPoint slides. Okay, here we go. Getting this. We'll go over here. Okay. You're talking about this, right, Dr. Strudel? Okay. Yes, I use that night light. I like that much better. Okay. So the first part is to get our state space model. So we have our states, x1, x2, x3. So our first step is to take the derivative of these. x1 dot, x2 dot, x3 dot. And then this is going to be equal to our A matrix times our states plus a B matrix times, well, we only have one input here, U of t. So just looking at this, here, I'll partition these out real quick. So the first equation, x1 dot, is 3 times x1 plus 2 times x2 plus 8 times x3 plus 1 times u of t. And then the other ones, I'm just blasting through this. So this is our A matrix, and this is our B matrix. Is that what you guys got? And then our output equation. Okay, good. Two outputs times our states, x1, x2, x3. Okay. U of t. So this is going to be a 2 by 3. This is going to be 1, 1, 0, 0, and 0, 0, 1, and then another 0 here. C matrix, D matrix. Okay, so could you go a little more in detail about that? Certainly. So we have two outputs. The first one I want to be x1 plus x2, and the second one I want to be x3. So what I'm going to do, I'm going to multiply out this matrix equation I wrote just to prove, hopefully, that that it's correct. So if I multiply out this, it's going to be 1 times x1 plus 1 times x2 plus 0 times x3 plus 0 times u of t. So that's doing this operation. And then if I go to the second row, I'm going to have 0 times x1 plus 0 times x2 plus 1 times x3 plus 0 times u of t. And so if you add that all up, you'll get back this x1 plus x2 and then x3. You're very welcome. What I like to do, if I'm ever confused about is my matrix correct or not, this is the process I'll go through. I'll just multiply out all my matrices and see if it adds up to what I know the output should be. And then eventually you just get, when you practice it enough, then it's just much easier to fill these in. But this is what I'm thinking as I go through it. What is the matrix multiplication going to look like? Did you want me to go through more of this, Dr. Strudel? Like, because the next part is getting the initial condition response and then the step response. Or was this what you were mainly interested in? Nope, that's right. Okay, cool. You're very, very welcome. What other questions do you guys have? Anything? My plan for this afternoon, first thing I'm going to put that project up. And then I'm going to try to get up as many homework solutions as I can. I got a little bit behind on the homework solutions and the homework grading. So I'm going to try to get those to you because I think that feedback is important. So my apologies for the delay.
About whom I'll work for. I simply have no other choice.
I see. Then let me ask you one question. In all your years forging weapons for other warriors, how many have inspired you to create such a weapon?
Let me think. I guess in all my years doing this, I'd have to say that there has been just one person whom I felt had reached the pinnacle of his craft as a warrior.
See, now I'm self-conscious about my PowerPoint lecture style. Oh, but you have colors in your PowerPoint, and you alternate back to writing stuff out by hand. You do a little bit of both. That's right, you use all the colors of the rainbow. Plus you're making it interactive. I think the danger with PowerPoint is when you're just reading it through and there's like no engagement. But you do not have a typical PowerPoint presentation. Asynchronous PowerPoint. Sounds lame. Yeah, if somebody just posted a PowerPoint and you're going through it. Personally, I've always felt like PowerPoint slides was like watching my family vacation photos in days of yore. Oh, man. And this is Phil and me at the Grand Canyon. Oh, man. No. That's funny. All right, everybody. I am going to sign off here. Get cracking on some other course-related stuff. I hope you guys have a great rest of your afternoon. If you're taking any other classes, I hope that's going well for you. Thank you for stopping in, UB Math Prof. You're not teaching tonight, are you? Or wait, yeah, you are. You do Tuesday, Wednesday, Thursday? If you guys are interested in linear algebra, that's what UB Math Prof is teaching this summer. Tuesdays, Wednesdays, Thursdays from 6:30 to 9:15, I believe. I've stopped in from time to time to just troll the channel, you know, just cause problems. Disarray and disorder. That's what I try to create. So, Discord, yeah. All right. That's it for me, my friends. Blessings on the rest.